Chapter 7, Recurrence Relations. Oh, this is a very useful thing, because in many situations, sequence has a recurrence relation. And if you know the recurrence relation, you can understand the sequence better, and you can find a formula for the sequence. So let's start with a motivating example. There are there is a pair of newborn rabbits. One male, one female, and each pair of rabbits, at least 2 months old, reproduces another pair of rabbits. Every month. Here is the assumption. And this pair will reproduce again if they are at least 2 months old. Then the question is, how many pairs of rabbits are there after n months? How many number of rabbit pairs after n months? This is the question. So the number of rabbits will grow quite quickly under this assumption, and we want to know exact number of pairs of rabbits after n months. So solution. So let's say an is this number. N is this number of rabbits after n months. What is A0? This means right now, how many pairs of rabbits do we have? Only one. It's newly born. What is A1? Let's try to compute the first few numbers in this sequence. Because it's only after 1 month, it's only 1 month old, so it cannot reproduce anything. So we don't have any new pair, so it's 1. But now, A2, we have a different situation. After 2 months, this newborn rabbit right now, but after 2 months, it will be 2 months old, so it will reproduce another pair. So we have 1 plus 1, so it's 2. Okay? So here, this 2 means we have 1 pair, 2 months old, and another pair, newly born pair. So in the 3rd month, what happens? This will produce another pair, because we assume that this is at least 2 months old. It will create, so by the way, no rabbit will die, right? They always live forever. So they are still there, and this will reproduce another pair, right? This part. So we have 1, 2, 3. So it's 3, etc. What about A4? Shall we do A4 more? So we have 3 here. 1, 2, 3. This part, they are now 2 months old, so they can reproduce. So this will reproduce 1 more. This will reproduce 1 more. So like this. So it will be 5, and etc. You can continue and then compute. And do you see any pattern here? And this is actually a very famous number called a Fibonacci number. And actually, AN is, you can consider this in the following way. It's the number of pairs in already there, let's say. And there will be new pairs, number of new pairs, right? Basically, always the situation is like this. After 1 month, then we have previous pairs, they are still here, and then there will be new pairs, newborn pair. So we have to add these two numbers. What is this? Number of pairs already there. That means number of pairs in previous month. So this is what? an minus 1, right? And what about this? Which pairs can reproduce? 2-month-old. That means the pairs which were already there 2 months ago, they will reproduce. So this is an minus 2. This is an minus 1. So we have this relation an equals an minus 1 plus an minus 2. So this is a sequence obtained by adding the two previous numbers. So here you see this is 1 plus 1, and this is 2 plus 1. This is 3 plus 2, and the next one will be 5 plus 3, 8, and then 8 plus 5, 13, and this plus this, 21, etc. It goes like this. So this is Fibonacci number. These are Fibonacci numbers. So this kind of relation is called a recurrence relation. And many important sequences have recurrence relations like this. So let me define what a recurrence relation is. So a recurrence relation for the sequence A0, A1, A2, etc. We have an infinite sequence like this. And a recurrence relation for this sequence is an equation. An equation relating an in terms of previous terms. Previous terms means A0, A1, am minus 1. So recurrence relation is a way of writing this nth term in terms of A1, A0, A1 up to am minus 1. So example, Fibonacci sequence that we saw. F1, yeah, it's a little different from the previous one. The index is shifted, but yeah. Sometimes we begin with A0, or sometimes we begin with 1. So in this case, in the textbook, we begin with 1. So these are initial conditions, and Fn equals Fn minus 1, Fn minus 2. You can see in this equation, we expressed this Fn in terms of previous terms, Fn minus 1, Fn minus 2. You don't have to use all the previous terms. And these are called initial conditions. And this is called the recurrence relation. So if you have initial conditions and recurrence relations, then you know what this sequence is. You can generate this sequence using the initial conditions and recurrence relation. So 1, 1, and then because you know that it satisfies this, the next one is the sum of this, next one is sum of this, like we did before. You can generate this sequence, and you can go as far as you want. Oh, I think I made a mistake previously. Okay. There are many examples of this. Fibonacci sequence is one famous one. Another one, very useful example, real life example, compounded interest. I think everyone knows this. In Korean, we say this 복리이자, 이율. So it means if you have interest, you get another interest coming from that. So a person invests, say, $1,000 at 12% interest, which is huge, right? Compounded annually. Then what's the amount of balance after the balance after n months, n years? This question is. So again, we say AN is the amount after n years. Of course, A0 is the initial investment. What is AN? Each year we have this 12% interest. So we have in the previous year we have this amount of money, and then we will get this interest. So it's 1 just times 1 plus 1 comma 1 2, 12%. And this is basically it. This is it. Recurrence relation. This is the recurrence relation. We express nth term using the previous terms. And this equation, this recurrence equation is the simplest possible, so we can get the nth term immediately. You know, if you use the recurrence relation again, a n minus 2 times 1.12 squared, etc. You can go all the way until the end, then we get a0 times 1.12 raised to nth power. So this means we know a0, so 1.12 to n 1000. After nth year, we will have this amount of money in the balance. Oh, by the way, once you are given initial condition and recurrence relation, and we know the sequence, but in this case, it was quite special, so we were able to write down nth term without using previous terms. We were able to write down an immediately, like this raised to the nth power times something. Very easy in this case. But in general, we don't always have this kind of situation. Sometimes it's difficult to write down nth term immediately. But we will learn when we can find such an explicit formula. This kind of thing is called solving the recurrence relation. So sometimes solving the equation is easy, but sometimes it's very difficult. Oh yeah, maybe I can tell you another very famous example. It's called the Tower of Hanoi. Yeah, when I was young, like maybe middle school or elementary school, I read an article like this. I was reading some textbook and maybe math textbook, I don't know. There was an interesting story. There was an old man in Hanoi, and he was claiming the following. He set up these three packs, and then 64 disks of all distinct size. So here is 64 disks. So here we have 3 towers, A, B, C. So their disks are like each of the disks has a small hole so that we can place on top of around this tower, this small pack. And what this old man claimed is the following. You are allowed to move one disk at a time, and you cannot place a bigger disk on top of a smaller one. You can always place a bigger one first, and then on top of it you can place a smaller one like that. This is okay, but you are not allowed to place a small one and then top one. Okay, this is not good. And your job is to move all of these 64 disks from A to, say, C, using only this kind of move allowed. One move at a time, and without putting a bigger one on top of a smaller one. That's the condition. And the claim, his claim, is that if you move all of these disks from A to C, then it will be the end of the Earth, end of our world. Our world will be destroyed if you move this over here. That's the end of our, not for just our lives, but the Earth will destroy. That was his claim. Can you believe it? So this is one way to destroy the universe. If you move all of this here to here, then you can destroy the universe. So why? Let's think about this and see if that really makes sense. Of course, if you just hear this for the first time, it sounds a little strange. Why? Because it doesn't look very difficult, right? Doesn't sound that difficult. But if you analyze this carefully, you will realize that actually he can be right. So let's see. So because 64 is just a special number, let's say there are n disks. And let's say an is the number of moves, necessary moves, moves needed to move n disks from A to C. So this is one peg to another peg. That's the. So what is A0? A0 is too simple. I mean, let's begin with 1. A1. Just one move is enough. You can just move that disk, just one disk to A to C. This one. What about A2? We have 2 here like this. First, we have to move. So here we have this. First, we have to move this to the smaller one here. First move is like that. The second move, we place this over here. Second, like this, and finally, we can move this here. We need 1, 2, 3. So 3 moves are required, and you can continue. We can find a simple recurrence relation. Let's compute an in terms of previous numbers. So imagine we have n disks, like this. There are n disks. So initial situation is like this, A, B, C. But if you want to move everything from here to here, we don't know exactly what we need to do, but at least for sure we can be sure about this. We have to move the biggest one, right? Because we have to move everything. But we want to place the biggest one at C. But because of the condition that we cannot place a bigger one on top of a smaller one, when we move the biggest one, this must be empty, right? The only case that we move the largest one from A to C is in this situation. The largest one here, and here is n-1 things are here, and this is empty. Only in this situation we can move the largest one from A to C, right? But how many moves do we need from here to here? Just imagine that this is just, ignore this because it's not moved at all. So we have n-1 disks, and we moved all of them from one peg to another peg. So this we need n-1 moves because we moved n-1 disk. We need n-1 moves. And after here, we can move this disk to this place. Here n-1, like this. So it's a +1. Here we need plus this many moves, plus 1 move. And finally, we can place all of this from here to here. That is another a n minus 1 moves. Biggest one and n minus 1, things like that. So here we need another a n minus 1 moves. Okay, is this okay? This means a n is equal to 2 times a n minus 1 plus 1. So like here, this number is 2 times this plus 1. The next number is 3 times 2 plus 1, 7, etc. So we found the recurrence relation and number. But how do we know a is 64? You can compute this like 64 times and you will get the number, but it will be very tedious. So let's try to compute the first few numbers. After we learn how to solve recurrence relations, we can solve this in a routine way, but because we don't know this yet, a1 equals 1. Let's try if we can find some pattern. So a2, what is a2? This times 2 plus 1 is 3. 3 times 2 plus 1 is 6 plus 1 is 7. And 14 plus 1, 15. 30 plus 1, 31. Do you see any pattern here? 62 plus 1, 63. Any pattern? Can you recognize any pattern here? You can see 32 minus 1, but 32 is 2 to the 5th minus 1. 64 is 2 to the 6th minus 1. Is 2 to the 4th minus 1. And from here you can see you have a clear pattern. So you can guess that an must be this, right? But this is not a proof. It's only a guess. If you want to prove this, you can prove this by induction. If you have a correct guess and recurrence relation, then proving that this is true in general is easy by induction. You can prove by induction. How? You know, n equals 1 is clearly true, or we have already done. Suppose this is true for n and n plus 1. What is n plus 1? Using the recurrence relation is 2 times an plus 1. But by the induction hypothesis, we assume that it's true for n. 2 to the n minus 1 plus 1. And here is, oh, it should be minus, right? Oh, is that right? Okay. Oh, no, sorry. Yeah, this is plus, right? The recurrence relation is plus, this is minus. So, yeah. So it's 2 to the n plus 1 minus 1. So it's true for n minus 1 case. So it's done by induction. So if you know, but sometimes this is not easy to guess. This one is very clear that we have this pattern, but sometimes pattern is not very clear. For instance, Fibonacci number. You don't really see the pattern. So what is A64? 2 to the 64 minus 1. So let's see how much time we need. So suppose that it takes 1 second to move one disk. One move takes 1 second, and then the total time will be this second, right? Or let's say this second. This is almost the same as this. You know, it's 2 to the 10th times 6 times 2 to the 4th, which is 16. But we know that this is 1024, which is almost 1000, so we can approximately say that this is 1006 and 16. So which is what? This is 1.6 times 10, so we have 18 plus 1, so it's 17 seconds. And so if you change this into years, it will be so this should be 9, right? 1.6 times 10 to the 19th divided by 1 hour is 6,300 seconds, and we have 24 hours a day and 365 days a year. So it takes this many years. And this is approximately 5,000. Okay. Years. So in Korean way, is that right? No. It's like if you divide this into 4 digits. So in Korean we say this is 5,000 억년, right? So it takes this much time, 5,000 억년, 5,000억 년. And scientists say that the age of Earth is 45억 년. This is the Earth, age of Earth. And age of the universe is 200억 년. Compared to this is much, much larger than this. So maybe it's true that after these many years, it may be destroyed. So the point here is that it takes a lot of time. You cannot really do this in your lifetime, and this tells us how quickly this power function grows. 64 doesn't seem to be a big number. 64 is even less than 100, but if you consider 2 to the 64, this is unimaginably large. Okay. So they are some examples, and now let's study recurrence relations in more details. Recurrence relations. Okay. So by definition, a recurrence relation is a way of writing nth term using previous terms. So we have an equation like this. For instance, Fibonacci number. Can we solve? How can we solve such a recurrence relation? First, we have to define what I mean by this solve. Solve means Fn equals something involving only n without using these previous terms. Like before, in the previous example, an equals a. This meant by solving this equation, recurrence relation means we write an explicit formula for an without using previous terms. We saw in the previous page, the example is 2 to the n plus 1. So this write down an explicit formula using only n, involving only n, without an or fn or anything like that. In this case, we were able to do this because we could find a pattern of this. We just wrote down the first few numbers, and then they exhibit like a clear pattern, so we were able to guess this, and then after you have a correct guess, proving is not difficult. But for recurrence relation like this, you don't really see any pattern there. It's kind of difficult. And if you look at the answer, then you will you will see you will never be able to guess this formula because it's not like this. Very strange formula here. After you're solving this, solving recurrence relations. In fact, last time we solved very simple two recurrence relations, something like an equals 2 times an, a minus 1, and a0 equals 1, something like that. Then we can immediately find the nth term like this. Then it's going to be 2 to the n. This is pretty clear. And also, we had this kind of thing where 2an minus 1 plus 1, and then a1 equals 1, something like that, right? And then from this, by computing the first few terms, we guessed that an should be 2 to the n minus 1. And then once you have a correct guess, then it's easy to prove by induction. But today, we will see more complicated recurrence relations, and it's not so easy to guess most of the times. So we will see how to solve recurrence relations, certain type of recurrence relations. There's a routine way to solve this. So let me begin with an example. The next page, maybe. So we have a recurrence relation like this: 3an minus 1 minus 2an minus 2, and the initial conditions are like this: a1 equals 1. All right. And let's see if we can solve this. So the idea is the following. Let's see this here. Maybe it was a mere coincidence, but it happened that this is equal to some power of n, right? As something raised to the n, and also something to raise it to the n. So we will guess that we will find a solution to this without worrying about these recurrence initial conditions. So in other words, if we can find, so we will find another sequence satisfying exactly the same recurrence relation. Find the sequence. So here is an observation. B0, B1, we will find another, probably simpler sequence which satisfies the same recurrence relation. Recurrence relation, meaning like Bn equals 3Bn minus 1 minus 2Bn minus 2. And the same initial conditions, meaning B0 equals 0, B1 equals 1. What can you say? Suppose that we have another sequence, seemingly different, B0, B1, B2, etc. But that we showed that the initial conditions are exactly the same, and B satisfies exactly the same recurrence relation. Then what can you conclude? They must be exactly the same sequence, right? Because a sequence is completely determined by its initial conditions and its recurrence relation. Then we can conclude that An must be equal to Bn, obviously, right? We will find a sequence satisfying both this and this, where we have an explicit formula for Bn. Then that gives us a formula for An. That's the idea. So let's see how we can prove this. So our another important observation here is that we will try to find a sequence of this form. Simple form, like Bn equals r to the n, where r is a constant. Okay. Let's say Bn equals R to the n and then see if this can really satisfy this recurrence relation. That's the idea. First, let's not worry about the initial conditions. And what does this mean? This, let's say this is the recurrence relation, and this implies what? We can just substitute this there. R to the n equals 3r to the n minus 1 minus 2 to the r minus, r, 2 times r to the n minus 2. If Bn, given by this number r to the n, if this sequence satisfies this, of course r must satisfy this. And here, from here, we divide both sides by the lowest power. Then we obtain r squared equals 3r minus 2, or in other words, r squared minus 3r minus 2, which is r minus 2 plus r plus, I think it should be plus, right? Minus 1 equals 0, right? If r satisfies this, so r satisfies this recurrence relation, I mean this equation, if and only if r satisfies this quadratic equation. So we know that if r equals 2 or r equals 1, then this sequence really does satisfy the recurrence relation. Is that correct? Then Bn satisfies star. It's okay, 2 to the n or 1 to the n, which is always 1. So here we found two different solutions to this recurrence relation, 2 to the n, 1 to the n. But important feature about this recurrence relation is that it's linear, meaning the coefficients are constant. So in this, so if, okay, so another observation. If Bn, say alpha to the n, set both Bn and Bn equals, say, beta to the n, both satisfy the recurrence relation here, then construct another sequence, say Cn, which is, say, A times alpha n, B times beta n, for any constant, A, B constant. This also satisfies star, right? Because if you have any two solutions, then their linear combination also satisfies that. Because, you can just substitute it there. In other words, for any constants A and B, this sequence, Cn, let's say Cn, A times, we just found 2 to the n, B times 1 to the n, which is always 1, always satisfies star for any choice of alpha A and B. But here we only found a sequence which satisfies the recurrence relation. We also want this to satisfy the two initial conditions. The first 0th term equals something and the first term equals something. And by choosing A and B carefully, we can make this to satisfy the initial conditions together. All right? So we want to find A and B such that the 0th term equals, what is the 0th term? 0. And the first term equals 1. Oh, sorry, this should be 0. But this is just a simple computation. Just let's put n equals 0. C0 equals a plus b. We want this to be 0. And C1 is 2a plus b. We want this to be 1. Now we can solve this to a system of equations, and then we get a and b. So if you solve this, what is a? A equals 1, b equals minus 1, I think, right? Then both let's write. That means if we say Cn equals 2 times n minus 1, then this is exactly what we want. An must be equal to Cn, because Cn satisfies the same recurrence relation, same initial conditions as A does. So A must be equal to C. But we know Cn equals 2 to the n minus 1. We are done. We just found a formula for An. And this idea generally works for any recurrence relation of that kind of form, linear recurrence relation. So let me summarize this as a theorem or with a definition. I just illustrated the idea behind this method. And let me state the definition and the theorem in a more clear way. So a linear recurrence relation, linear and homogeneous recurrence relation is a recurrence relation of this form. An equals C1 An minus 1 plus C2 An minus 2 plus dot 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 CR An minus R, where R is a constant, fixed number, fixed integer, and C1 dot 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 CR are constants. They are fixed numbers, like the recurrence relation that we saw, like An equals 3An minus 1 minus 2An minus 2, something like that. So this is the definition. Linear means these are constants. Homogeneous means we don't have any extra term here. So basically it means something like this. And in this recurrence relation, the characteristic polynomial is the following. Characteristic polynomial is a polynomial of this form: x to the r minus c1 x r minus 1 minus c2 x r minus 2 minus dot 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 minus cr equals 0. This is the characteristic polynomial. This is the equation that is obtained by putting an equals x to the n and then divide both sides by the lowest power of x. Okay. And theorem is the following. So what is the degree of this polynomial? The degree is r. So it has at most d root. It has d roots. Maybe there are multiple roots. But if S1, S2, dot dot dot, SR, if this characteristic polynomial has distinct roots, all distinct roots, of the characteristic polynomial, then we can always write An as a linear combination of their powers. So let's say alpha 1 S1 squared, alpha 2 S2 squared, it should be n. Power of the roots are S r to the n for some constants. Alpha 1 dot dot dot. We can always find these constants alpha 1 up to alpha r so that an equals this. So initial condition, if the linear homogeneous recurrence relation looks like this, we need initial conditions, a0, a1, dot, 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 ar minus 1. We must have r initial conditions. But it can be given arbitrarily. But no matter how these values are given, you can always find constants so that an satisfy both the recurrence relation and the initial condition. That means we can just write down the nth term immediately like this. Okay? So this is a very useful theorem. As long as you can find the distinct roots of the characteristic polynomial. It's routine. It's just a routine computation to write down the nth term. So now let's try to find the nth term of a Fibonacci number. So example, Fibonacci number is given by this. f0 equals 0, f1 equals 1. Okay? Now we want to find nth term of this. It is almost impossible to guess if you just compute the first few terms. So solution. It's very it's a routine solution. So what is the characteristic polynomial here? So it is a linear recurrence relation, homogeneous. So and degree is 2. So x squared minus x minus 1 equals 0. Okay? What is the solutions of this? So x is 1 plus or minus square root of 1 minus 4 ac, so which is 5, over 2. So there are two solutions, two distinct solutions. So it satisfies the condition for the theorem. That means Fn, we must be able to find alpha and beta such that the general solution must look like this. For some constants alpha and beta. All we need to do now is to find these two constants. How can you find these constants? Using the two initial conditions. Okay? What is f0 from here? It's alpha plus beta. This is 0, right? And f1 is alpha times 2 to the 1 plus square root of 5 over 2 plus beta times 1 minus square root of 5 over 2. This must be equal to 1. Okay? Now from this we know that beta is minus alpha, so you plug in beta equals minus alpha here, then what do we get? These two will disappear. So alpha, so alpha square root of 5 times alpha equals 1, right? So alpha equals 1 over square root of 5, and beta equals minus 1 over square root of 5. So Fn is equal to 1 over square root of 5, 1 plus square root of 5 over 2 to the end, minus 1 over square root of 5, 1 minus square root of 5 over 2 to the end. So this is the general formula for nth term. And as you can see, it's kind of interesting because Fn is always an integer, must be an integer, but we have irrational number, square root of 5, involved. But it turns out that for every non-negative integer n, it must be an integer. Okay? Now, how can you guess this formula without knowing this? It's very interesting. Okay, so here you may have some questions because here in this theorem we have some condition. We have all distinct roots, but not every quadratic or cubic equation have distinct roots. Sometimes we have multiple roots, double roots or triple roots. This cannot be applied in that case. But fortunately for us, we have another theorem. But before stating the theorem, let's see what happens if we have multiple root. Minus 2, h0 equals 0, h1 equals 1. Here, the characteristic polynomial is x squared minus 4x minus plus 4. So it's x minus 2 squared equals 0. So we have a double root, 2. We only have 2. So you cannot really find, maybe if you are lucky, you can find such a solution, but you just try to do exactly the same thing, but here, this is just alpha plus beta times 2 to the n, so it's just a one constant. We have only sort of one degree of freedom. If you are lucky, maybe this is good, but most of the time, this will not be enough. So we need two distinct solutions. So if we have two distinct roots, we will get two distinct solutions, but for a double root, we have only one solution from the root, power of root. But there is a theorem. Theorem. If the characteristic polynomial has roots with multiplicity, like double root or triple roots, etc., we can still do the following. So for instance, suppose that the roots are like this, considering the multiplicity together. So we have root alpha 1 of multiplicity m1, right? So for instance, here, 2 is a root with multiplicity 2. So alpha 2 dot 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 alpha 2 m2 multiplicity. So we have r distinct roots, and their multiplicities are given as well. A1, so alpha 1, the multiplicity is m1, multiplicity of alpha 2 is m2, etc. If the multiplicities are all 1, then it reduces to the previous theorem. Distinct roots. Then an is the nth term of the linear recurrence relation is, from this alpha 1, we need to obtain m1 distinct roots, but they are just like this. So c11 alpha 1 to the n, c12. Here we have n alpha 1 raised to n instead of alpha n. And then you can just n squared alpha 1. It goes like that. C1 m1 and m1 minus 1 alpha 1 n. In other words, these are distinct roots coming from alpha 1 if the multiplicity is m1. So you can see we have 1, 2, 3 up to m1. m1 distinct roots. And this is for alpha 1. And of course, we have to continue. 2, 1, alpha 2, and c 2, 2, and alpha 2 squared plus dot 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 c2 m2 and m sub 2 minus 1 alpha 2 to the n, and it continues, and at the end we have cr1 alpha r and cr2. This looks very complicated because I'm writing the general situation. N alpha r to the n. But the idea is like this. CR mr n to the mr minus 1 alpha. The idea is these are distinct roots. I mean, these are distinct solutions to the recurrence relation. So if you have multiplicities, all you need to do is to multiply n to this power of alpha. one at a time until you have used all the multiplicity. So, for example, so let's solve this example using the theorem here. I'm going to use the next page. So hn equals 4hn minus 1 minus 4hn, hn minus 2, h0, 0, h1 equals 1. Characteristic polynomial, we found that is equals 0. That means we must be able to find a solution like this: alpha times 2 to the n, beta times n times 2 to the n. We should be able to find two constants, alpha and beta. How? Just using this initial condition. h0 equals alpha, just alpha, right? This is 0. h2 equals h1. 2 times alpha plus 2 times beta equals 1. So we know alpha equals 0, so beta equals 1 over 2. So hn is, substitute alpha equals 0, beta equals 1 over 2, then we get n times 2 to the n minus 1. So this is the solution. Okay. For those who have taken the course differential equation, then you may have seen something like this. You know, if you remember, y double prime, differential equation looks like this. I don't know, a y prime minus b equals 0, right? Then you say y is, you have a characteristic you find a characteristic polynomial x squared minus, okay, maybe I should use something else instead of x. The characteristic polynomial is t squared minus at, or maybe m, I think. You used m. M squared minus ma minus b equals 0. You solve for m, and then if m equals alpha and beta, then you say it is like e to the alpha x, and you have some constant r and then some constant beta x, something like that. Then we must have a solution like this if you have taken a differential equation. Very similar. And if we have a double root here, then instead of this, you have r e to the alpha x, and then s times r as a constant, x times e to the alpha x, something like that. So this looks very similar to recurrence relation. This is not a coincidence. There is a very close connection between differential equations and linear recurrence relation in terms of generating function. So this, I'm not going to tell you the details, but if you write, you know Taylor series, right? If you have a sequence A0, A1, dot, 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 then you can write down, how can I say, n equals 0 to infinity. You can write, this is called the generating function for this. And differential equation really correspond to recurrence relation there. And I think yeah, maybe you should use this exponential generating function. But anyway, there is a close connection between recurrence relations, finding the solutions of recurrence relations, and the finding solutions of differential equation. They are very, very close. They're almost the same.